All right, so I want to put some graphs up on the board that I think are elementary graphs. You absolutely need to know, especially A and B. Okay? Somebody should be able to shake you up from an afternoon nap and say, graph 1 over x. And you should be able to graph it just like that. And then say, let me go back to sleep or something. But you need to know this graph without thinking. Okay? You need to know it that well. Okay? So what does the graph of 1 over x look like? It is the reciprocal function. Its graph looks something like this. Okay, notice how I just graphed this. I put on it the two ordered pairs that I knew. What's the reciprocal of 1? 1. What's the multiplicative reciprocal of negative 1? What is the reciprocal of 2? And you could plot this thing. What is the reciprocal? What's the reciprocal of 1/10? 10. What's the reciprocal of 1/1000th? 1,000. The closer and closer I get to 0 from the right, what happens to my y values? What's that?
Goes to infinity.
Yeah, the y values get arbitrarily large as I get closer and closer to 0 coming from the right. Okay? So this graph has both horizontal and vertical asymptotes. We find the vertical asymptote by exploring the behavior near x equals 0. We find the horizontal asymptotes by looking at the behavior as x gets large, either large positive or large negative. Okay? What does the graph of 1 over x squared look like? We graphed this just the other day. The graph of this function looks like this. What does the graph of 1 over x cubed look like? Well, when I plug in a 1, what does it spit out? 1. If I plug in a large number like 100, cube 100, how big is that? Big. Divide that into 1, what do you get?
So small.
Small number, right? So as I go further and further to the right, my y values get very, very small, approaching 0. What if I approach 0, though? It goes up like this. Okay. And sure enough, this is the graph of the other one. Folks, how did A and C compare? They look similar. Are they the same? No. Okay. Specifically, that green function rises up more quickly as we approach the asymptote, and it dies off more quickly. It goes to 0 more quickly. Okay. But the general shape of those two functions is the same, and that's what I want you to notice going forward. Okay. What do you think the graph of 1 over x to the 4th looks like?
Similar to B.
Yeah, so it's going to be similar to B. Not exactly the same. Okay, it's going to rise up more quickly and die off more quickly. Okay. All right. So here's some basic facts. Some of these we've already seen. I'm trying to put both the 2.4 and 2.5 facts together on one page, just so you can contrast them. Okay. So let's say I have a natural number and I've got 1 over x raised to a natural number. Then this graph has a vertical asymptote at x equals 0. Do you agree? When I look at the limit as x approaches 0, I will either get infinity or minus infinity depending on my direction of approach and depending on the function. Okay. In fact, if n is even, like 1 over x squared or 1 over x to the 4th, then as I approach 0, I'm always going to get what, regardless of the direction of approach? Positive infinity. We always get an arbitrary large number. But if the function is odd, then I'm going to get out either infinity or minus infinity, but the direction of approach matters, right? As I approach 0 from the right, I get out positive infinity, but as I approach 0 from the left, I get out negative infinity. So that's all that's being summarized in that statement right there. Okay? As a reminder, we can remember these above limits by the phrase 1 over a small positive number approaches infinity, and 1 over a small negative approaches negative infinity. Okay? Now, this is just a recap of section 2.4. Okay, that's what we did, that's what you've been working on. Okay. The new material is here. If I just have 1 over x to the r for any rational number r, okay, as x gets large, where do the y values get close to? If I have 1 over x to the third and I plug in a big number for x, what am I going to get?
Small number.
Something that's getting close to
0.
0. Okay? So if I put 1 over x to the r, and I say I'm going to plug in a big number for x, what am I going to get?
Small number.
A small number, something that's approaching 0. That's all I'm saying here. Okay? So as x approaches infinity, or as x approaches negative infinity, that expression tends towards 0. So that gives me a what? Horizontal asymptote. Okay? All right? Now, we can take this one step further by saying, hey, not only, it doesn't even have to look like 1 over x to the r, it could be some shifting of that expression too, and it'll still go to 0. So this statement here, I know that looks a little confusing. What I'm saying is if I asked you what's the limit as x approaches infinity of, say, I don't know, 2 over 3x seventh minus 6, what's that going to approach?
0.
It's going to approach 0. You can use that fact. That fact, you can just go ahead and say, I know that to be 0, because it's just based on a transformation of these elementary graphs. Okay? Because this function right here that I put up, this function right here, is just a transformation. It's just a combination transformation of those elementary graphs. So it's still, as you plug in large numbers, still has a horizontal asymptote at y equals 0. Okay? All right, so we remember this phrase by 1 over a large positive number approaches what? 1 over a large number approaches what? 0. And 1 over a large negative approaches what as well? 0. Doesn't matter if it's positive or negative. Okay. Okay, folks, so here's our trick for dealing with limits at infinity. So anyway, when you deal with limits at infinity, okay, i.e. when you're looking at the limit as x approaches infinity of f of x, the trick to dealing with this is to multiply by 1 over x to the highest power seen in the denominator. One over x raised to the highest power seen in the denominator. Okay? Over itself. I guess we'll stab back.